The objective of this video is to calculate the tangential and normal air gap fields and current linkage that are created by a surface current density. And as a review, we've been talking about surface current densities on the inner bore of our stator. We've talked about this as two equivalent representations. One representation being a circumferential current density, where we talk about the total number of ampere turns at any given angle. And the second being a linear current density, where we consider the ampere turns per meter or per linear length. And we can relate these two quantities. In a previous video, we developed the equivalent circumferential current density for a three-phase winding system as being this equation here. And in a separate video, we have related our linear current density to our circumferential current density by noting that the linear current density is going to be the circumferential current density divided by the radius. In this video, we're going to derive expressions for the fields that are created, both the tangential field and the normal field, and then the current linkage in the normal direction. So let's start with the tangential fields. And this one is easy. We've talked about in a previous video how a linear current density creates a tangential field in the air gap. Now let's do the harder one. We're going to talk about normal fields and the current linkage. And to do this, we have to go back to Ampere's law and the Maxwell's equation that the divergence of B is equal to 0. So we'll be evaluating Ampere's law over an Amperian loop. And let's sketch what that loop looks like. I'm just going to draw a fraction of a stator. So I think you know what I mean at this point in the class. So we're drawing a quarter of a stator and a rotor. This is our rotor over here. And we have this large air gap. And then on the inner bore of our stator, we've got a current density. And I'm just drawing this in a general sense, just to show that there is some distribution of current on that inner bore of the stator. So if we construct an Amperian loop to evaluate Ampere's law, we could construct a loop like this, where you travel radially across the air gap, radially back in, and we're assuming in this whole derivation that we've got a sinusoidal circumferential current density. So we'll go radially outwards at an angle alpha 0, and we'll come back in at some angle alpha. So evaluating Ampere's law, we're again going to assume, like we always do, that the H field does not vary with our length, so it can come outside that integral, and that we've got infinite permeability in our back iron, so that H field is 0 in the iron regions. And this quantity is equal to the current enclosed in that loop, which is a line integral over the circumferential, it's an integral over the arc of the circumferential current density, from alpha 0 to alpha. And if we write this as an expression for Hn of alpha in terms of all the other quantities on the right-hand side, we get this expression. Okay, great. This is reminiscent of the building block model that we developed for a single coil. We've got H of alpha in terms of our current density, which is a good thing, because we know our linear current density, so we can evaluate this part. However, at the moment, we don't know what value to use for alpha 0, and we also don't know what Hn of alpha 0 is. So in order to resolve this, we need to impose that the divergence of B is equal to 0. And we can make our lives a lot simpler when we evaluate this integral if we pick the value of alpha 0 to be such that this whole cosine term drops out. So if we intelligently choose a value of alpha 0, we are left with one less term in this expression. And here you can see the value that we should select for alpha 0 to achieve this. So if we do this, we can now evaluate the integral and enforce that it must be equal to 0. And when we do this integral, we can see that this term right here has to cancel out. It has to go to 0. The integral of any cosine over an integer multiple of its periods, so we're integrating from 0 to 2 pi, because n is an integer, this has to be equal to 0. There's no way it can't be. It has to be 0. And what we can conclude from this, then, is that 2 pi times Hn of alpha 0 must equal 0, and therefore Hn of alpha 0 equals 0. And so we can go back to this expression and evaluate what Hn of alpha is. And we can use this to determine what our current linkage is. As you recall, current linkage is going to be hn of alpha times the air gap length. And from this, we can calculate what our magnetic field is in the air gap. So we have our three normal components here. Let's also summarize our tangential component. And all of this is true for when we have a circumferential current density of this form. So in conclusion, in this video, we've talked about how we can take an equivalent linear current density or circumferential current density, but an equivalent current density on the inner surface of our stator, and use that equivalent current density to calculate the tangential and normal air gap fields and the current linkage that's created. And so our grand finale was this big blue box here of all the normal H field, B field, and current linkage components, and then the tangential B component.